Swayam Prabha, free DTH channel for education.
Greetings. We will discuss dense coding in this class. After we have already discussed teleportation, which is to communicate this piece of quantum information which Alice had, and we managed to figure out how this can be teleported to Bob, who is at a remote location. And this information could be teleported using entanglement, which is always there. It's not something which has to beat the speed of light, because it's not information which you send from one end to the other end, but that information is always there in the entangled species. So that's the Bell state. And it is this property that we used in achieving teleportation without compromising the limits of the special theory of relativity. What we are going to discuss in this class is dense coding, and that suggests that you're going to pack more information than what is normally considered to be possible. And the information that we are going to consider in this context is about two classical bits. This is not a qubit. These are two classical bits. It is not a superposition. If you have a superposition of 0 and 1, with some arbitrary coefficient so that it is some point on the Bloch sphere, then you do not know those coefficients. And that is a quantum bit of information. That is what makes it a qubit. Here we are talking about classical bits. These are two switches, on or off, 1 or 0. And these two classical bits are with Alice, and she wants to send information and tell Bob that I have a pair of classical bits. But of course, what pair is it? Is it 0 and 0, or 0 and 1, or 1 and 0 and 1 and 1? So there are different possibilities of these classical bits. So these are classical bits. This is a pair of classical bits. One is 0, the other is 0, and so on. So these are the four possibilities, and Alice has one of these pairs. But Bob doesn't know which pair it is. Alice knows which pair it is. These classical bits are with Alice, and she intends to send this information over to Bob, but she's going to use only one quantum bit to communicate this information. And that is where the normal limit of coding comes in, because in the normal limit, it is not possible to send this information using a single qubit. So can she achieve this using a single qubit? So the key word over here, which puts the limit of what is the normal density, is using a single qubit. She is to communicate information about the pair of her classical bits to Bob. And what puts this limit is a theorem in quantum information science, which is called as Holevos's theorem, was a Russian scientist. And Holevos's theorem states that a single qubit can communicate no more than one bit of classical information. So that's the limit. And what does Alice want to do? She wants to send information about two classical bits. She has two classical bits. She has a pair of two classical bits. And this is the information that she wants to send and let Bob know about which particular pair she has. So she's going to send information about two classical bits, but Holloway's theorem tells you that a single qubit can communicate no more than one bit of classical information, and she must use only a single qubit. If she is able to do it, then it is beating the normal limit, and this is what is called as dense or super dense coding. And you can use entanglement in some ancillary support, in some additional infrastructure that Alice and Bob can use, but the actual information which she will communicate would involve a single qubit, and that will amount to beating the Holloway limit, which is why it is called as dense coding. So this is the pair of classical bits that Alice has, and she must use no more than a single qubit, but they do have some additional resource with that. What do they have? They have a pair of qubits with them in a Bell state. These are correlated qubits, and it can, however, be any one of these four Bell states. We have discussed that there can be four different Bell states. And what Alice and Bob have with them is a Bell state, two qubits, which are maximally correlated. They cannot be factored into direct product or a tensor product of individual qubit vectors. It can only be written as a correlated entangled two qubit vector. And we have used the symbol beta for Bell earlier. This is the Bell state of qubit 1 and qubit 2, and the letter pi over here in the subscript tells the parallel combination. This is with reference to spin qubits. Of course, the qubits can be anything, any physical system which offers itself to be a qubit can be used. And the representation of the qubit in terms of the spin qubit would be either both are up or both are down. And the chance that the qubit with Alice is up or down is exactly half. So it's totally random. But it is guaranteed that if Alice has up, then Bob also has up. And if Alice has down, then Bob also has down. So that's the correlation in this entangled two qubit vector. And it comes with a plus sign. The two possibilities over here, one with a plus sign and one with a minus sign. And for the sake of our discussion, we presume that the Bell state, in which Alice and Bob have a two qubit system with them, second qubit with Bob and first qubit with Alice, is this particular Bell state. Now, Alice has got qubit number 1, and what she would do to do dense coding is to perform single qubit gate operations. Single qubit, she has one of the two qubits which are in a Bell state, and on this she will perform a quantum gate operation. It is in a state of entanglement, so it will obviously impact the qubit which is with Bob, and then he can do some further analysis with that, which is what we will be discussing. But which particular operation she has done is something which Bob must know. And then she has to communicate this to Bob, but not using anything more than a single qubit. That is the Holloway limit. So our question is dense coding possible? Can we beat the Holloway's theorem? And this is not really beating the Holloway's theorem. It is working beyond the limitation of the Holloway's theorem, but using some additional resource, which is this Bell state. It is like what we did in the case of teleportation also, that in a certain sense we managed to use entanglement, which doesn't require any time to lapse between sending information and receiving it, because the information in the entangled species is always there. And that's not the same thing as breaking the limit of the special theory of relativity. So this is also in a certain sense not going to violate the Holloway theorem, but within the limits of the Holloway theorem, whatever coding is possible, that limit will be broken using additional ancillary resources through this Bell state. But she must not use more than one qubit to achieve this. So these are the classical bits with Alice. She has two classical bits, 0, 0, 0, 1, 1, 0, or 1, 1. And they have an initial Bell state. This is our initial condition. Alice has got the qubit, and her qubit is over here. The second qubit is with Bob, and that is at a different location. And Alice would perform single qubit gate operation on her qubit. That is in her possession. Even if Bob is away, he is at a remote location, he could be in a different galaxy, it doesn't matter. But Alice has her single qubit, and on this qubit, she will perform a gate operation. And subsequently, Alice would teleport information, or she will send this quantum of information. A single quantum channel will be used for this. And using that qubit, Bob will then figure out which of these 4 pairs of classical bits she has. So single qubit is all she will be using. And if she manages to send information about 2 classical bits, then it is dense coding. It is in a certain sense going beyond the Holloway limit, but using some additional resources of Bell states. So this is our initial state. And what Alice would do is that if she has this pair of classical bits, she has one of these 4. If she has this, she does nothing. It's like performing an identity operation, which will leave the Bell state invariant. So this is one possibility. She could also have a different pair of classical bits, in which case she could do something else. So if she does the identity, then it leaves the qubit. Her qubit consists of this 0 and this 1, and this qubit remains in the same state. It doesn't get changed because she does nothing. It is like performing an identity operation. And the transformed qubit, which I denote by a prime, is essentially the same as the initial qubit, which is phi. And the initial qubit and the final qubit are the same. So it is like performing an identity operation on the initial qubit. And after the gate operation, which is the unit matrix. So this is one possibility. And this is what she would do if the pair that she has is 0, 0. However, she may have something else. So if she has 0, 0, she applies the identity operation. If she has 0, 1, then Alice would apply the poly not gate. If she has 1, 0, she applies the IY gate. And you remember the poly not gate the poly Y gate. You do the poly Y gate and then multiply it by I. And then finally, if she has the fourth possibility that the classical bits that she has are both 1, 1, then she applies the Z gate. And this is something that they have decided between them. That depending on which pair of classical bits she has, she is going to apply this. But Bob doesn't know which pair she has, and therefore he does not know which of these gates operations Alice would perform. And that information is something that Alice can send him through 1 qubit and no more than 1 qubit. So Alice is going to do some single qubit gate operation. And you remember the single qubit gates. These are represented by various matrices. The poly NOT gate or the poly X gate or the poly Y gate and the poly Z gate. These come from, they carry poly's name because of poly matrices which we use in denoting the intrinsic angular momentum of the electron, the intrinsic spin half angular momentum of the electron. And she could also use the Hadamard gate. We have discussed these single qubit gates earlier in some of our previous discussions. And Alice could use any of these single qubit gates. So what she's going to do in this case is to use the poly NOT gate. The first case is when she would not do anything, which is to apply the identity gate. In the second case, she would use the poly NOT gate. And what does the poly NOT gate do? It flips the 0 into 1 and 1 into 0. It is like rotating the Bloch sphere about the x-axis. So this is the result of the quantum NOT gate, which we have discussed well earlier. In the Bloch representation, 0 and 1 are collinear, but essentially you remember that 0 and 1 are orthogonal in the vector space. And this is like a cartoon. It shows orthogonality, but then you have to remember that they are orthogonal in the vector space, which is not our usual geometry anyway. On the Bloch representation, the orthogonal states appear as collinear. One is on the North Pole and the other is on the South Pole along the same line. And that is what allows you to represent any arbitrary combination of 0 and 1 by a point on the Bloch sphere. And what the poly NOT gate does is to rotate the Bloch sphere about the x-axis. So this is what the poly NOT gate would do. And if Alice is to apply poly NOT gate to her qubit, then the states of these vectors, this 0 would flip into 1 and this 1 will flip to 0, right? So this is the case we are considering. The first case we already considered. In this case, Alice would do nothing. In this case, poly NOT gate will be used by Alice. And what the poly NOT gate would do is to change 0, 1 to 1, 0. This is the NOT operation represented by the poly X matrix. And as an application of the poly NOT gate on the original qubit, on the, hello? Hello? If the poly NOT gate is operated on this vector, you get a new vector in which Alice's 0 will go to 1 and Alice's 1 will go to 0. So these are the vectors 0 and 1. The states of these will change to 1 and 0. Bob's remain unaffected. So Bob's 0 remains 0 as it is. So this original Bell state gets transformed into a different Bell state. This was a Bell state which we denoted with the subscript pi, because in this both are up and both are down, whereas over here in this Bell state, one is down, the other is up. If this is up, this is down, and this one is with a plus sign. So this Bell state gets transformed into a different Bell state. And this is the result of applying the poly NOT gate on the qubit which is with Alice. So in the third case, Alice has got two classical bits, 1 and 0. And in this case, Alice would apply the IY gate. So you know the poly Y gate, and then there is a further multiplication by I. So the IY gate is to be applied. First, we will remind ourselves of what the Y gate does. So this is coming from the poly Y matrix, which is 0 minus I 0. And the IY gate is like the NOT gate with multiplication with plus or minus I. So this is the result of the IY gate. So this is what the Y gate does. What does the Y gate does? Because Y gate has got 0, minus I, 1, I, and 0 over here. It will change the vector 1, 0 to 0, 1, but it will multiply it by I. So 1, 0 going to 0, 1 is like a NOT operation. So alpha goes to beta, but it also gets multiplied by I. So this is different from the poly X gate. And the 0, 1, the beta goes to alpha. So that is again like the NOT gate, but then it also get multiplied by minus I. This is what the Y gate alone would do. But what are we doing? We are doing Y gate with a further multiplication by I. So IY gate will be like a NOT gate, and multiplication not with plus or minus I, but plus or minus I square, which is like minus or plus 1. So this is the effect of the IY gate. So first, this is the impact of the Y gate itself, and the IY gate changes alpha to beta. So this is like a NOT operation, but with a minus sign here, and beta to alpha, this is like the usual NOT. But together, it is not the NOT gate because this sign has changed, but only the sign of beta becomes minus, this remains plus. So this is to be done carefully, keeping track of the signs. So this is the third case that we are discussing, 1, 0. This is the pair of classical bits which Alice has, and Alice now applies the IY gate, as a result of which alpha goes to minus beta, beta goes to plus alpha, and therefore this 0 goes to minus 1 and this 1 goes to 0. So this is the result of the IY gate. So you get again a Bell state, but a different one. So the original Bell state is transformed into a new Bell state, but which new Bell state it would get transformed into depends on what operation has been carried out by Alice. In the first case, she did nothing, which is like executing the identity gate. In the second case, she applied the poly NOT gate. In the third case, she applied the IY gate. And the fourth case, which is coming up now, in the fourth case, she has 1, 1. This is a pair of classical bits. The two classical bits that she has are 1, 1. And in this case, what Alice would now do is to apply the poly Z gate to her qubit. And you remember what the poly Z gate does is to change the phase of the qubit because it multiplies the second one by -1. So essentially it is like rotating the Bloch sphere about the z-axis through pi. So it is a phase gate. It changes the phase of the south pole, right? So this is what you get. And the reason it changes is because the direction of the plus x positive x-axis reverses under this rotation about the z-axis of the Bloch sphere. So as a result of this, the z gate flips the phase. The azimuthal angle is with respect to the zx plane, but the zx plane is the half zx plane. So the zx plane with only the side which has x greater than 0. And that side has now been reversed because of the rotation of the Bloch sphere about the z-axis through 180 degrees. So this is what Alice is doing now. She has got two classical bits which are 1 and 1. She applies the Pauli Z gate, as a result of which keep track of this minus sign over here, which means that this 0 will remain this 0, but this 1 remains 1 with a minus sign. Okay, so that is the change of phase that she has achieved. And this is the information which is now coded in the Bell state. It is now coded in the Bell state because the original Bell state is now transformed to a different Bell state. So let us sort of compile this information, consolidate that together. So Alice has got a pair of classical bits, this one or this one or this one or this one. And depending on which pair she has, she performs either the unit operation or the Pauli naught or the Pauli y multiplied by I, which is the IY, or the Pauli z. And the original vector phi, the original Bell state, gets transformed to a new Bell state, which is phi prime. But the phi prime is different in these cases. So this is 0, 0 plus 1, 1. This is 1, 0 plus 0, 1. This is 0, 1 minus 1, 0. And this is 0, 0 minus 1, 1. So these are 4 different Bell states. And which pair of classical bits are with Alice? That information is now coded over here. Now, coding has been achieved. But what does Bob know about it? Bob has to be given some hint. Some information has to be communicated to him because Bob doesn't know which pair of classical bits are with Alice, and therefore he does not know whether Alice has performed this operation or this operation or this operation or this operation. And this information is to be transacted to Bob using no more than a single qubit. That is the Holevo limit. And that is the challenge which is still to be addressed. So the Bell state is transformed, but it is transformed conditionally depending on which gate operation has been carried out by Alice. And she can convey this information using 1 qubit. That is the allowance. And the Holevo limit is that if she's communicating information using 1 qubit, then it cannot carry any more information than about a single classical bit. That is the Holevo's theorem. And what we are trying to achieve is to pass this single qubit to Bob, but convey to him information about 2 classical bits which Alice has. So this is something that we are trying to achieve, which is why this is called as dense or super dense coding, which is going beyond the Holevo limit. And this information is now coded in this Bell state. And there are 4 possible Bell states depending on what Alice has done. And what Alice does depends on whether she has this pair or this pair or this pair or this pair. And that results in the original qubit, original Bell state. This is the original Bell state which Alice and Bob had, but now they are in different locations. Bob is far away in some other galaxy or wherever. And Alice now may send 1 qubit of information to Bob. And from that, Bob has to figure out which pair of classical bits she has. So let us see how this is to be done. So what Bob now does, he has some resources. He may be anywhere in some other galaxy, but he has got a very nice laboratory and he can perform gate operations himself. So what he's going to do, that he will use the qubit he has received from Alice. Alice is allowed to send 1 qubit, okay, within the Holevo limit, but she sends 1 qubit of information to Bob. And Bob now has this qubit which he has received from Alice. And Bob uses that as a control qubit and performs a control NOT operation on his qubit. So Bob effectively has both the qubits, and he uses the one that he has received from Alice as a control qubit, and he performs the control NOT operation on his qubit, which is a 2 qubit operation. And let us see what kind of information he can extract from this. So he performs a control NOT on the Bell state. It is a Bell state, but he does not know which of the 4 Bell states it is. And if the Bell state is this particular one, then as a result of the control NOT operates on this 5 prime and gives him a new 2 qubit vector. And this is not an entangled 2 qubit vector. It can be factored. This is a Bell state, but not after it is operated upon by a control NOT gate. What the control NOT is doing, the control NOT operation, is removing the entanglement. So the control NOT destroys the entanglement and gives you a 2 qubit vector, which can in fact be factored. So this is the result of the control NOT on this Bell state. You get a factorizable 2 qubit vector. If the Bell state is this, which is the second case, then the control NOT disentangles it and gives you a new 2 qubit vector, which is also factorizable. If the qubit is, the Bell state is this, then you get a new 2 qubit vector, which is again factorizable. And the same thing happens over here in the 4th case. So there are 4 different Bell states, and there can be no more than 4 different Bell states. Then the control NOT will give you in each case a factorizable 2 qubit vector. It removes the entanglement. You remember that the control NOT serves as an entangler, but also as a detangler, as sometimes it is called. So it has detangled the Bell states. And this is the detangled 2 qubit vector. This is factorizable. This is with a double prime. The single prime one was the one which Alice got after operating on her qubit with a single qubit gate. So now you get a 2 qubit factorizable vector. And there are 4 possibilities which correspond to the different pairs, different possible pairs of classical bits which are with aleph. These are the 4 possibilities which I have written in the middle. But then these are factorizable, and let us write those factors. What are those factors? This 2-qubit vector is a tensor product, a direct product of this with this. So this is the original qubit which Bob had. This is the qubit. This is what has happened to the qubit as a result of the control knot. This is not the original qubit that he got from Alice, but this is coming from the factorizable states, and this comes from the part which has come from Alice, and this factor is either 0 plus 1 for the case 1, 1 plus 0 for the case 2, 0 minus 1 for the case 3, and minus 1 plus 0 for the case 4. Now, Bob really has some of the information that he wanted to get, which is to identify which of these 4 pairs of classical bits, 2 classical bits, Alice has. If Bob finds that his qubit is 0, so it could be this case, but it need not be only this case, because look at this one, the 4th one. This is also 0. So if Bob measures his second qubit to be 0, then the pair of classical bits with Alice is either 0, 0 or 1, 1. He can rule out possibility 2 and possibility 3, but he still doesn't know whether it is 0, 0 or 1, 1. He knows that it is not 2 and 3. It's not 0, 1 or 1, 0. But he doesn't know whether it is 0, 0 or 1, 1, because there are these 2 Bell states, which have been rendered factorizable after the performance of the control knot operation using Alice's qubit as the control qubit and Bob's qubit as the target qubit. As a result of this, the factorizable states are these, and Bob now has half of the information. He knows, he rules out 2 possibilities, but he's still confused. He doesn't know whether it is 0, 0 or 1, 1, which is the pair of classical bits which Alice has. However, between 1 and 4, okay, and 2 and 3, so there are these phase differences, because if Bob gets 0, he knows that it is either possibility 1 or 4. Likewise, if he gets 1, then he knows that it is either 2 or 3, because in both cases, 2 or 3, Bob has got 1 over here. 1 is with Bob. This is also 1 with Bob. And in both cases, he gets the state 1. But then the factor is different, because this one is with a plus sign and this one is with a minus sign. And now what can he use? Can you think about it? So he has to distinguish between case 1 and case 4. He has ruled out 2 and 3. And if he gets 1, he rules out case 1 and case 4, but he doesn't know whether it is case 2 or case 3. In other words, he has to find what kind of a combination, what kind of a linear superposition is it? Is it with a plus sign in between or a minus sign between? Essentially, these signs have to be different in this pair, because you can always pull out an overall minus sign and absorb it in the normalization. So the linear combinations in 2 and 3 are different. And likewise, the linear combination in 1 and 4 are different. And this is where he can use the Hadamard gate. So Bob can pass the first factor, which is this factor, through the Hadamard gate. And the Hadamard gate will tell him whether it is a superposition with a plus sign or a superposition with a minus sign, because that is something that the Hadamard distinguishes. And let me remind you quickly what the Hadamard gate is. So this is the matrix which represents the Hadamard gate. And the Hadamard gate, if it operates on a pure 0, then it gives you a superposition of 0 and 1. If it operates on a pure 1, it again gives you a superposition of 1 and 0. But mind you, they are different superpositions. In the first case, you have a superposition with a plus sign in between. In the second case, you have a minus sign in between. So the Hadamard is sensitive to this sign. It converts a pure state into a mixed state. And then if you apply it again, it converts a mixed state into a pure state. So a Hadamard, when you operate it twice, it gives you a unit matrix. So it can distinguish between this plus sign and minus sign. And now Hadamard gate will make a distinction between case 2 and 3. It will also make a distinction between case 1 and 4. And using this, Bob now finally gets the complete information that we wanted Alice to communicate to Bob using a single qubit, which is dense coding beyond the Holevo limit. So thank you very much. I will stop here and we will do one more exercise in the next class about dense coding. Thank you all very much.
Thank you, sir.
Goodbye for
Thank
now.
you, sir. Thank you, sir.